Okay, so let us get into the last few topics on this unsupervised learning module. And now we are going to talk about diffusion models. And I'm going to cover these slides a bit quickly because we are short of time. But I'll try to touch upon all the main ideas in both diffusion models and flow matching models. So, you might have already seen diffusion models. We all have seen a stable diffusion, mid-journey, DALI. These are dominant text-to-image models which have, recently you might have seen samples from them. Imagine is one more, and you also have these diffusion models being used in audio and speech synthesis. The modality is different, and some other more unique applications which also exist. Okay, so I will come to the details of this intuition. What you are actually trying to do is you add a bit of noise to the image again and again, and then make the model learn to undo it at every step. So this is a very high level explanation, but the important thing is to understand why it should work. Okay, the noise, why the model is able to learn the level of noise, and why adding noise of a certain kind is useful. So obviously, the idea is that the model is learning how to unblur a certain image to look at the sharper version, and therefore in that process it also given your training set, it also learns something about the underlying distribution, and we'll see how. uh, and during inference, essentially you can start from a completely noisy image, which is equivalent to your sample from a standard normal distribution, and you can iteratively refine it to generate a sample from your image distribution. So that's the idea. And obviously the sample quality is great, and the stable and the training objective is much more stable. In fact, for both diffusion and flow models, you'll see that the training objective is stable. Okay. So these are a recent class of models which can be motivated in from VAEs themselves. Okay, so they can be looked upon as hierarchical VAEs, and you will also see the idea of transformation of random variables being applied, and the idea of flow. So which essentially is learning a sequence of transformations as a function of time. And the main point that I'm trying to make here is if you have a random sample which is sampled from a simple distribution, we've seen this again and again. If you have this, right, then can we repeatedly transform it? So can we continuously do this, right? So you have g theta of z, and then you have x dash, which is g dash theta of x, and so on. If you keep on doing this, right, will there come a point where the sequence of x's that I have will start resembling my data? Okay, or the distribution of this final sequence is going to have a distribution similar to my data. So that's the idea. Okay, so so let us recall a few things from the VAE. If you remember, I said that in a VAE, there is an encoder network, okay? And it takes an input sample X and it gives you a latent Z, right? And usually this is a D-dimensional vector, this is an M-dimensional vector, and D is greater than M, right? Now, what you are saying is that your input distribution is some very complicated P of X, but in a VAE, what you expect is that this distribution should be a standard normal. And uh, intuitively it is difficult to achieve in a single step. It makes sense, right? You are if this was a very high complexity encoder, maybe infinite complexity, maybe this was possible. Okay, but we have some finite complexity encoders, and there is a huge constraint which is there. So now, instead of doing that, let us suppose that we take t encoding steps. Okay, so you start from X, which is your input sample, and you do X1, X2, X3, and so on, and get up till a point of X capital T, which now I'm denoting Z as X capital T. Okay, so which is finally Gaussian, right? So now what I'm doing is, instead of using the letter Z, I'm using the letter X capital T, okay, which is the random variable at the capital T each step. Okay, so you started from your input and you took capital T number of steps to get to X of T, which has a standard normal distribution. Okay, now in each step you are doing a certain kind of encoding. Okay, so what you can easily expect is that possibly this X of T will be more Gaussian, okay, than compared to X1 or X2 and so on, because you are doing the transformation slowly, right? And therefore, at each step t, we take the current latent x of t minus 1. Okay, now, so now you have this, right? You have x of t minus 1, and that goes through some transformation, okay, like an encoder, and you have x of t. Okay, so from the point of view of this teeth step, right? This is the input and this is the latent, and that is why all intermediate x's, right? We can call them as latents with respect to their input. Okay, so you take x of t minus 1 and you get the next latent x of t. Okay, now one special case that happens in diffusion models is uh, although we do repeated encodings similar to a VAE, but we use the same dimension. Okay, so the x's are in the same dimension as the original input. Okay, so that the reduction in dimension is not being done. So the same is shown in this figure here. Unfortunately, the figure has z's, but you can think of this as x1, x2, and x of t. Okay, and you are doing this, right? You are going from x to x1, x1 to x2, and so on up till you get x of t. Okay, what this transformation is going to be is something that we'll discuss, right? For the case of vanilla diffusion models. Okay, so now, what I had shown you before was a forward diffusion process. You take your input sample and you repeatedly corrupt it to get to a point where your sample has become completely Gaussian. Okay, so in case of vanilla diffusion models, there is a deterministic process which goes from each previous step to each next step. Okay, and uh, in the vanilla diffusion models, all you do is that x of t is a noisier version of xt minus 1. So this is the forward diffusion which is done. You just take a random Gaussian sample, you scale it, and you add it to the previous sample. Okay, so all you're doing is you're adding noise to this one. Okay, this Gaussian sample acts as a noise vector, and you scale both of them according to some levels, and you add it. So x of t is simply this. Okay, now in distributional terms, if you look at this equation, right, all that it means is you are given x of t minus 1, okay, and you want to generate x of t. Once you do that, the x of t is going to have a distribution like this. Okay, so x of t will be centered at this mean, right, and it will have a variance which corresponds to the variance of this thing. Okay, so that is because of the nature of this equation that x of t is going to have a distribution like this. So the same thing I have also shown here. You can see that this is the distribution of the input data. Okay, if I keep adding noise to it, okay, this is also something which comes up often in signal processing. If you are adding an independent random variable, two independent random variables, the result is the resulting distribution is a convolution of the two. And for any image processing folks, you would know that convolving any function like this with a Gaussian is going to smoothen it. Okay, so you see a smooth version of this one, you see a smooth version of this one, you keep on adding noise, right? And finally you get the most smooth version, which is just standard normal. Okay, so this is your forward diffusion process. So now all this is fine, right? So this is a deterministic process. There is there was no neural network involved. Okay, you can just keep adding noise based on some levels which I had shown as alpha. Now comes the reverse process, and this is where neural networks come in. Okay, for the reverse process, what we will do is that we will have a generator or a decoder. Okay, so now I'm using these terms interchangeably, but this is more like a decoder of VAE. So now what you have is that you have something like this, right? I'm drawing it in reverse. So you have x of t as the input, and you have x of t minus 1. Okay, so you are basically going from this latent back to this input space for that time step, and therefore it's sort of like a decoder. Okay, and the mathematics is such that this generator or a decoder, right? So the reason it's also called generator is because it's going to finally generate the sample of interest for you when you iteratively run through it. So what will happen is that when you do the reverse process, right? When you try to make the neural network essentially take this x of t, okay, and you will also give this information of time, and you make it predict x of t minus 1. Okay, intuitively it should try to remove the noise. Okay, whatever noise was there, right, it will try to remove that epsilon and then try to predict x of t minus 1. Okay, so that process is also going to result in a reverse distribution, okay, which now is parameterized by theta, which is your neural network. What it is going to do is that it is going to give this kind of Gaussian normal again. Okay, and the neural network is only going to predict the mean of this. Okay, so the way the equations are set up are such that your neural network, given at input at any time step, predicts the mean of the distribution at the previous time step. Okay, so this way what you are doing is you, okay, so fine, you gave x of t, this thing is going to give you some, mu theta of x of t comma t. Okay, you take that distribution, sample xt minus 1 from it, right? So you can sample from it, and whatever is there. Okay, so you can sample from this distribution, and then you get x of t minus 1, you again go back. So that is something that can be done at a very high level. Okay, although we'll refine it further, but this is the main idea. Okay, uh, so I'm not going to go into the details of this equation. I have kept it here for completion. But you can, if you go back to our VAE discussion, right? This is essentially again log likelihood, and this whole thing is again elbow. Okay, this whole thing after on the RHS is again elbow, and you will see that the first two terms. This is the reconstruction term of VAE. This is the KL term of VAE. Only thing is that now instead of Z, you have x of t and p of x of t, which is supposed to be standard normal. The only new term is this one, and this is called the denoising matching term. Okay, this is the most important term. And here, what you are doing is that you construct a distribution. Okay, given, so you have your input x of 0. Okay, and at any step t, right? Suppose this is your neural network theta, and you have x of t coming in. So you take both of these, right? You take both of these. This is anyway available. Okay. And then you also give the timestamp so that the neural network knows which time step it is working on. And then it tries to predict x of t minus 1. Okay. So that's the only thing that it is doing. Okay. So this is the reason I explained why this is called a denoising matching term, is because the neural network is trying to remove the noise. Okay. And this is the same as VAE. We make this simplification. Okay. Now, as it turns out that the equations are such that the denoising matching term can also be simplified. Okay. You can either have the neural network predict the original sample x0, which is the original input, from the tth version of it. Okay, or you can predict the noise epsilon, okay, which was used from x0 to go to its tth version. Okay, so when everything is Gaussian and you're only adding Gaussian noise, okay, the whole setup gets simplified to for the neural network to only predict the amount of noise which was required to reach x of t. Remember that this is already known, right? Your forward diffusion process already knows the epsilon noise which has to be passed, right? So the denoising matching term can be written like this. You have some scaling factor. This is the epsilon noise which you had to add repeatedly, right? So you went from x0 to x1 and so on up till x of t. And so the total amount of noise that is added here, okay, is known. Okay, now what you want the neural network to do is take this x of t, Okay, take the time and predict this noise, right? So you compare these two and you want to minimize this so that the neural network understands how much noise was added. And there's also something that I've shown here. So you may have a neural network which is a sort of shape of a unit, okay, which takes in an image, reconstructs an image, and you want to be able to tell how much amount of noise is there in this particular input. So, as it turns out, this particular term, the denoising matching term, is the most important in this equation. The other things are already well known from BAE. Okay, so I think I've already explained that. You add a tiny smudge of noise. You essentially try to understand, make the neural network understand what is the level of noise. So there are other ways to explain this, but let us leave it at that. Okay. Uh, So obviously the objective is stable because at every step you are asking only for a reconstruction of the loss, which is basically just predicting the amount of noise. So the MSE is between either the noise or you may just be predicting the input from the TH step directly. So in both cases, it's a stable training objective. All right. So suppose you have uh, trained diffusion model. Okay. Then what do you do? Okay. So essentially what will happen is uh, you will do what is known as ancestral sampling in statistics. So first, sorry, you will sample from a standard normal distribution. Okay, so you will sample one xt from here. So you take one sample, call it x of t. Okay, now what you will do is you will pass it through your uh, okay, you will pass it through your decoder or generator network. It will give you the amount of noise which is available. Is there in this. Okay, now you take this and you update it to, so you remove this noise and you get it gets updated to x of t minus 1, right? And you keep on doing this again. You pass it through theta and tell that now I am at time step t minus 1. It will again give you some amount of noise which might be there at this time step. You subtract that noise from this one and keep going. So iteratively you keep on doing that until you reach x of 0, which is your final sample. So this is essentially what I've written. The only thing is that for some amount of diversity, right, we also add a random noise term. Okay, so you can see that in the distribution space, right, you are continuously sampling something. You sample x of t minus 1, you x of t minus 2, right? So you are basically going through a trajectory from the distribution of x of t till the final distribution p of x0, which is our input data distribution, which I hopefully it has learned, right? So you're traversing a trajectory, and this noise term, random noise term, helps give some diversity to that trajectory. Okay, so just going back to to make my point. So if you look at this figure, right, you start from here. Suppose you start from this sample. This is your x of t, right? And when the neural network denoises it, you come here, x of t minus 1. Maybe you come here, x of t minus 2. You come here, you come here, and finally you come here. So it's essentially a trajectory that you are following in the data space. Okay. Okay. So one more associated topic that I quickly want to cover is the idea of scores. Okay, so scores are not new, but they are useful, and we'll see that the diffusion, the denoising matching term can also be rewritten in terms of scores. So this is something that you may read if you read about diffusion models. Put very simply, if you have a distribution of any input, okay, you take the gradient of that distribution, of the log of that distribution, and that is known as score function. So this is the definition. It is the derivative of log of a density. Okay. Now it points to the direction of steepest increase in likelihood. That is the regions of higher probability. Okay. So if you have so I can give you example of this Gaussian. So this is a one-dimensional Gaussian. You take a log, okay, and you differentiate it with respect to x to get the score function. Okay. So now if you have a Gaussian here, right, you can see that your score function is going to be right, and the score is 0 here. Okay, for it will be positive here, maybe some positive value. Okay, since it is increasing, right? So yeah, it will increase something like this, and it will be negative here. Okay, so what happens is that if you get a score here, you understand that you are on the right side of the Gaussian. You have taken a sample on the right side. To move towards the peak of the Gaussian, you need to move here. Okay, so it gives a positive gradient here. Whereas if you have a sample here, right, to move towards the peak, you have to go this side. So it gives a negative gradient here. Okay, so a score function ideally tells you in which direction you need to move. Obviously, it's a derivative, right? So that's expected, right? In which direction you want to move to be able to reach a peak of a distribution where most of the samples would be coming from. Okay. So, and the generic definition is here for higher dimensions. Okay, so as it turns out that the kind of formulation that we have for score function, right? Uh, the denoising matching term, which was given like this initially, right? It can also be formulated in terms of a score. Okay, so this is the score of a Gaussian, and it can be shown that the denoising matching term is simply trying to match the score of uh, the data distribution. Okay, so you look at this. Okay, this is your forward uh, diffusion process. I took the score of that. So I'm moving from x0 to xt by adding some noise, and the score of the xt distribution is going to be this one. So it's basically, if you look at it, right, it's basically in it's some sort of a directional vector, right, between x0 and xt. Okay, and what your model learns to do is essentially learn this vector, right? So either in this direction or this direction, it doesn't matter. The model tends to learn the direction of mm, the direction in which you want to move to go from xt to x0. So this is the direction that you get. Okay, and this is your neural network model. You take xt and t, and it learns this particular direction. Okay, so so essentially, like I said, right, you have a trajectory. You have xt plus 1, and you move from xt and this and this. So if all these directions are being learned by the model, right, then it is essentially learning a trajectory to move from x of t up till x of 0, right? This is your final this one. So, so there is a trajectory being learned, and this is what is important. This will essentially connect us to what is done in flow matching, okay, where you actually explicitly define these trajectories and you learn them. Okay, so this brings us to this quick detour on diffusion models. They can be seen as hierarchical VAEs, okay, with t number of steps of denoising, and uh, and there is a shared decoder, so it's only the reverse diffusion step which acts as a like a decoder of VAE, which tries to predict for all time steps. So it's shared in the sense that for all time steps only a single network is going to predict what is the denoised version. So forward process was hard coded, and the reverse process is what you train, and it's a single network. Okay, again there is an elbow which is uh, uh, which is optimized. Okay, and you just do a mean squared error on noise prediction. Okay, implicitly we have seen that the denoising actually also tries to learn the score function, which is you learn the score function at every noise levels. For each x of t, right, there is a different score function because there is a different distribution. X of t and x of t plus 1 will have different levels of noise and therefore different distributions, and the model learns to point to x of 0 from each of those. Okay, so the only trade-off here in case of diffusion models is the fact that they tend to be slow. You need to have take t number of steps to be able to generate a single image, and there are methods at inference time which try to speed it up, okay, based on more empirical understanding of the models and so on. Right. So now with this, we come to the last topic, which is flow matching, and I will quickly go through flow matching based on the ideas that we talked about in score function. So you already have diffusion, and we have already seen this, and the way I explained, right, you have some sort of sample from a Gaussian distribution, okay, which is x of t, and what you are doing is you go to x of t minus 1, you go to x of t minus 2, and so on, right, t minus 3, and finally at after t steps you do x of 0. Okay, now the way that this trajectory is constructed, right, in case of diffusion, uh, in case of diffusion, that was explicitly stated by how you're adding noise and creating Gaussian distributions in the forward process. It turns out that it is much simpler to actually just choose this trajectory. Okay, so we build this trajectory, and each of them, by the way, will have their own probability distribution, P of x of t, which is standard normal. You have x of t minus 1, right? So what the model is doing is it is essentially learning a probability path. Okay, it is learning how to move from this to this and so on up till P of x. Okay, and this turns out to be much more simpler explanation of how we can do diffusion, and also how we can build more models in this class. Okay, so so subscripts, so one thing is that yes, I will, whenever you see subscripts now, it is not sample number or anything, it is going to be time. Okay. If you remember, like I said, in the reverse diffusion process, you sample from the standard normal and you denoise it iteratively, right? So uh, I also explained that at each time step c from t to 0, you are sampling from a different distribution. Okay, so whatever new sample the neural network generates, it's actually a sample from a different distribution p of x of t. Okay, so it is able to traverse a trajectory of a connected set of distributions p of t, okay, with t equal to 0 to capital T. Okay, so here what I'm saying is p of capital T is my standard normal, okay, from which we got x of t, and p of 0 is my input data distribution from which my real samples were, data set was there on which the model was trained. Okay, so now with this notion, let us look at flow-based generative models. So now, just for clarity, one more thing that I think I missed is that in now we will have t to lie between 0 and 1. Okay, like I said, instead of between 0 and t. Okay, and therefore uh, at uh, t equal to 1, right, is your data distribution. So all x1s are data distributions, all x0s are your standard normal distributions. Okay, so let us suppose you sample from your standard normal, okay, and repeatedly transform until we reach the p of x1 distribution, which is our data distribution, right? So now, with this idea, what we can do is that we can define a set of transformations. So you saw that this idea of traversing the trajectory was there in diffusion models, but I am redefining it as a transformation of random variables. Okay, so what I'm saying is I'm just modeling the reverse process of diffusion models. Okay, you have a standard Gaussian sample. Okay, you transform it using a tth transform to be able to get x of t. Okay, where t can be between 0 and 1. So you basically have many transformations. Okay, now this transformation is what is known as flow. Okay, and the ODE, The ODE which dictates this transformation is defined like this. Okay, so we essentially go another step, and what we want to see is we want to see the velocity of this flow, velocity of this transformation. Okay, so the velocity is always a derivative. Okay, so I can always define something like this. Okay, let us say that at every step when you move from t equal to maybe 0 to t equal to maybe something like 0.5, right? There is a direction in which you need to move and the speed at which you need to move, right? So, this particular vector, okay, is what I'm defining here as the flow velocity. Okay, you can also look at it in this particular diagram. So this is at t equal to 0. Okay, you have some distribution which is given here, and this is your 2D input space, right? So this is the input space which is two-dimensional. So here x is element of R2, right? And the small arrows that you see here are the velocities, and the dots that you see is the flow. Okay, so any vector, any sample which is here, right, it must move here at this point. Okay, then maybe this is some intermediate t, okay, between 0 and 1. Okay, and sorry, not, maybe not equal to 0. So here, if you have a sample here, it needs to move in this direction. So what we tell the neural network to do is to learn these arrows. Okay, and the underlying distribution that is getting learned is this, what is shown by this contour. So as you move from t equal to 0 to t equal to 1, okay, the model moves from these distributions. Okay, so like I described, you carry out continuous transformations of the random variable, go from x0 to x of t and so on. Okay, and it will result in a random variable with a different distribution. Okay, so each of these distributions I am denoting by p of t, and I am setting them up as an ordered set, right? And this is what is known as a probability path. Okay, so these are a sequence of distributions, ordered sequence from t going to from 0 to 1, with the constraint that p of 0 has to be standard normal and p of 1 has to be your data distribution. You define this p of t. Okay, so once these p of t are defined, right, your phi of t will get fixed, and your u of t, which is basically the flow velocity, is also going to get fixed. So now, in case of diffusion, you have seen that all these p of t were some sort of Gaussian with different means and some scaled unit variance. Okay, so now what we make the neural networks do is learn the velocity. Okay, so for any x of t generated by, we make it learn the velocity such that any x of t which is generated by this velocity will follow the required distribution p of t. Okay, so if you are moving from, suppose, x of 0 to some x of t, right, we know the distribution of this, we want to learn this, and this we want that it should have a distribution p of t. Okay, so with these constraints, right, we are able to uh, formulate a flow matching loss. Here what happens is, you will have some velocity which needs to be learned to get to this point. You will make the neural network learn that particular velocity. Okay, so during training, this x of t is going to be available. Okay, and we'll see how it is. And obviously during inference, these x of t's are generated. So let us look at how to get this p of t, and that will result in how we get this velocity u of t. In fact, we've already seen that we also constructed a probability path in forward and reverse diffusion models. So similar to that, the simplest way to construct a velocity path, a probability path, would be actually to start from the input data. Okay, so you start from the input data and you corrupt it to get to the point t, right? So now your input data state set x of 1, okay, instead of x of 0 in diffusion models in the forward diffusion, and then you corrupt it to get x of t. Okay, you corrupt it with Gaussian noise, and you essentially have a P of t which is conditional. Okay, so what I'm saying is I have x of 1, I corrupt it to maybe get to this point which is x of t. Okay, so that can be seen as a combination of your input data sample and a noise sample, right? Now when you have this simple formulation, this u of t is again simple. It is just the direction between x1 and xt, the scaled direction between x1 and xt. So you are basically just looking at this direction, right? And now it turns out that uh, with this conditioning on the input sample, right, you have a flow matching loss which is actually computable. Okay, you have this velocity that is a function of input. Okay, you take this x of t and try to predict that velocity using neural network, and this is all the mean squared error. Okay, so this objective gets simplified to the neural network taking x of t, okay, and just predicting the direction between x1 and xt. Okay, so now if you recall, this is very similar to the score function. Okay, all you're doing is you're again predicting some sort of direction between the input sample and the current sample. Okay, so it is this objective which is known as conditional flow matching, because you are conditioning on an input. Okay, and you have the kind of path you have constructed results in a velocity which is learned like this. So you can construct different paths now. In case of diffusion model, there was a one specific path that was there. Okay. So this is the objective which is used to train a neural network for all time steps. Again, we may be taking many time steps to learn to get here, and then resample to get here. Okay, so sorry, let me rephrase. Actually, in case of flow models, we'll just be learning some random time steps, okay, as interpolation between complete Gaussian and this input data. And in all of them, you'll be using this. Okay, so the inference using flow models is easy to do. Okay, once you have learned this velocity, right? You recall the ancestral sampling that we were doing, right? All we need to do is something similar to that. You have a simple ordinary differential equation. You have a simple differential equation in which you have learned this part. Okay, so now you can just use Euler method. Okay, so this is basically you are at a certain position, you take some delta t time step, multiply it with velocity, you will get to the new position. Okay, so this is just the first order Taylor expansion or the Euler ODE solver. Okay, so this is how it works. You first take an input from the standard normal. Okay. Then for each of the discrete time steps that you have, so you will decide the number of steps you want to take to generate, and for that will divide your time interval into some delta t time steps. You keep on recursively updating this, where the velocity is coming from the neural network theta. Okay, and finally x1 is the generated sample. So if you have larger n, you will have to take many steps, but because delta t's will be small, so you may have more accurate results. Okay, and there are higher order solvers. You can basically add your other del t of square and other terms and those kinds of things, which can be there, which can reduce the step count but give us a similar quality. So the main thing is that you have learned the velocity of moving through this trajectory. Okay, so this brings us to the end of everything, in fact. So the flow matching generational method relies on solving an ordinary differential equation, a deterministic flow, which is from the noise to the data. So think of flow as transformation of random variables. It trains a neural network to generate the velocity field, which is the derivative of flow. Now, conditional flow matching loss is tractable, okay, very similar to score function, and it takes simple linear paths from the noise sample x0 to the data sample x1. Sampling during inference can simply be done by Euler solver, okay, which solves ODEs, and the number of steps are actually much lower as compared to those required by diffusion for the same quality. And this obviously is tightly connected to diffusion. In fact, it can be shown that diffusions are a special case of flow models for certain choice of your probability path. Uh, And again, flux flow, and these are the fast, high quality data generation methods which currently are state of the art. All right, so this brings us to the end of the unsupervised learning module. I hope I was able to give you some insights into how these high-end modules, these latest deep generative models are actually functioning. Overall, you will see that they are only applying a deep learning framework on top of a mathematical framework, where we decide what is it that the neural network should learn. In certain cases it may be velocities like in flow, in other cases it may be, for example, predicting the error in diffusion, okay, or predicting a certain distribution. So that's all from my side. Thank you for listening. Have a great day.